Hello, I'm Dr. Abhishek Sharma. Today we will discuss theory of random variable. Now, a random scenario leads to a different terms. Various engineering applications are used in different scenarios, which gives the different outputs as per their random characteristics. To understand these random scenarios, we consider the theory of probability, and random variable is a subsection of this probability theory. The most important term to discuss any random scenario is a random variable. A random variable can be defined as a random variable is a real valued function defined over the sample space of a random experiment. Now, in this definition, there are three key points. One of them is hidden. The first point is sample space, and another point is random experiment. The hidden point is the event. Now, to understand the random variables, or you can say the theory of random variables, let us first discuss it with a suitable example by which we can clearly understand different scenarios that how a random variable theory is applicable in real scenarios. So first we discuss few definitions related to the random variable. First definition is sample space. The sample space is a collective outcome of a random experiment. Now the second definition is sample point. A particular sample point is a subset of sample space, or you can say that a particular outcome from a sample space is called a sample point. Now the third definition is the definition of the event. Event is a collective outcome event may be a subset of sample space. Now let us consider an example. Suppose three fair coins have been tossed. Now the sample space for the collective outcome can be expressed as S. It may be that outcome have three heads and other several possibilities are head, tail, head, tail, head, 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 tail, 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 head, tail, 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 head, and finally tail, tail, and tail. Now let us suppose that we have to count the number of heads in each outcome. Point to be noted, number of heads in each outcome. In this example, it is very easy. For example, the first outcome have three heads, the second one have two heads, and so on. 2, 2, 1, 1, 1, and 0. Now suppose there are more than 200 coins, and in that case, if you have to find the number of heads in each outcome, then it will be very tedious. So in these type of cases, we first take our task as a random variable, which is the number of heads. Now in this example, we will understand how. Now the random variable for this example will be number of heads. Now to understand this example rigorously, we first calculate the probability of each outcome. Now since coin is fair, the probability for each of the outcome will be equal to 1 by 8. Again, the probability that the outcome have no heads can be calculated as P of x equal to 0. That means no head. And what is the case in the above example? It is this one. Suppose this is x1, x2, x3, x4, x5, 6, 7 and 8. Then x of 8 is the case when there will be no head. And the probability will be only one case is there out of 8, that will be 1 upon 8. Now the probability that the outcome have one head can be calculated as probability that your outcome has only one head, it will be equal to, then you have to consider again then how much outcome only have one, that is x5, x6 and x7 are the three outcomes in which only one head is there. So P of x equal to 1, that means only one head count, it will be probability of x equal to 5, 6 and 7. That means x equal to x of 5 plus p of x equal to x of 6 and plus p of x equal to x of 7. Now it will be equal to 1 upon 8 plus 1 upon 8 plus 1 upon 8. It will give you 3 upon 8. And again, the probability that the outcome of two heads can be calculated as p of x equal to 2. What it indicates? Two heads in the outcome. And it will be calculated as, in this example, the two heads are x2, x3 and x4. In these cases, the outcome have only two heads. Now we can write it as p of x equal to x2 plus p of x equal to x3 plus p of x equal to x of 4. It will be calculated as 1 by 8 plus 1 by 8 plus 1 by 8, which is equal to 3 by 8. Now finally, the outcome has all three heads. Then it can be calculated as p of x equal to 3. That will be equal to, in this case, this x1 is the outcome which have on all three heads. That means p of x equal to 3 will be equal to p of, when capital X is equal to x of 1. As this is the only one case out of 8, that means 1 upon 8 is the probability. Now arranging the outcome of the event with the respective probabilities in increasing order, x 0, 1, 2 and 3. It denotes the number of heads in an increasing order. Now f of x will be 1 by 8, 3 by 8, 3 by 8 and 1 by 8 again. From the above example, it is clear that fx, which is the distribution of capital X, have some specific properties. Number one is fx is always greater than or equal to 0, and the second is the summation of fx is always equal to 1 for every x. These two properties are very important properties. The function which follow the above properties can be considered as probability density function. In this case, fx will be considered as probability density function or probability function. This fx can also be considered as probability mass function. Now random variable lead to a very important property which is considered as probability density function. The behavior of the random axis, the random variable, can be continuous or discrete. That means random variable, there are basically two types of random variable according to the behavior. For example, it may be discrete, it may be continuous. To understand this, if we want to measure the temperature of a room throughout the day, the temperature continuously varies from a certain amount of temperature to another certain value. But this variation will be continuous. So this example leads to a continuous random variable. If a random variable is defined for this example, then it is said to be a continuous RV or random variable. And the relative probability density function will also be considered as continuous probability density function. Now, the probability density function for continuous random variable can be defined as f of x is equal to 0 and integral from minus infinity to plus infinity f of xx dx is equal to 1. So these are the properties related to the probability mass function. Every probability mass function, or you can say probability density function, must follow these two properties.